Thank you very much. So it is great pleasure to have opportunity here to give Russell Marker lecture. So today's talk is representing really another aspect of my work that during the past maybe 10 years or so. So our lab did a lot of work on random matrices and its applications to factor analysis and so on. So you'll see that just like most of my research is getting started from somewhere on my application and then driven as deeper and deeper. Now with with enormous amount of data, so people are thinking about how we can do let's say distributed computing and distributed estimation with statistical guarantees. So this is really a continuation of my talk yesterday. Oh, that's okay. Listen, It's on. Maybe this one. Not the. Okay. All right. So I'll give you an introduction, and then I'll tell you about distributed PCA, and then we use the analysis, and finally, I hope through numerical illustration you get an idea. What really I'm talking about. So this part is just a recapture of what we said yesterday on the massive data and distributed learning. So we all know that big data is everywhere, from internet to government to business, biological sciences and sciences. So what you heard most and successful story from is on business, because people do prediction and they create value quickly. But in science, really just as important, if not more important, to really getting the value from the day. And in terms of size, we know that before 2003, through the dawn theorization through 2003, we have 5 EB of data, and now every 2 days we could get that amount of data. And this certainly has huge impact on storage, communication, computation, architecture, as well as on the analysis part, like statistical computing, optimization, and privacy. And for me, being as a statistician, really I'm interested in 2 ends of the spectrum. One end, if you talk to any, let's say, government industry leaders, so they're really very concerned on privacy and ownership issues. I give data to Xingyuan or Ethan, I cannot guarantee how Ethan going to use it. Ethan going to give to another person, and so on. So even though he's my friend, I still have concern. So privacy is a concern, ownership is a concern. Now, so in addition to solve the problem of, let's say, storage issues, right? So I could distribute in different machines. I also say multiple copies, and the computation issues, because I ask each node machine to compute. So it's a distributed computing. But the beauty of statistical part of analysis is that we can do non-invasive analysis. So in other words, I do not need to, let's say, own genes data in order to analyze it. Gene analyze the data according to my protocol, and then just send me the results. Right? So among a huge amount of data he sent me, the result may be just regression coefficient, gradients, Hessian matrix is already too big. Okay, so and so on. So this is really have an impact on, let's say, statistical analysis too. And as I said, the collective efforts among different fields trying to solve these kind of issues is what I understand nowadays called data science. Right? So driven by the applications of many fields, from science to business to government and so on. So data science core issue is on data acquisition and storage, as well as communication, data analysis, and the computation associated with these kind of data mining, data analysis issues. And then, of course, what is the ideal thing that we would like to have, right? So data scientist's dream, to me, is really to develop efficient algorithms or efficient methods that computable in polynomial time and also important, it has to be communicable. Right? So from here, when I say efficient, I'm really referring to statistical efficiency. Right? So you should have high statistical efficiency, and this is really talking about algorithm complexity. Right? So it has to be computable in polynomial time so that we can get a realistic computation. And typically, because size is so big, we have to know distribute computing in many machines, and then you cannot just communicate a huge amount of, let's say, a billion hashing matrix. And this is only one round of communication. Next round, another billion hashing matrix. Right? It's impossible. So this is data science dream. And to me, this simple architecture that I'm drawing here actually is one method, a very simple method that actually solves many of the problems that I talk here. In particular, I do here in red. It's not mean that it's more important. It just means that this simple distributed architecture at least help us solve storage issues. And if you communicate efficiently, it helps us communication issues, right? I distribute all computation through different node machines, so help us computation issues. And lastly, privacy issues, right? So it is non-innovative, non-invasive analysis of your data. So this is really the beauty of this simple architecture. And today, my talk is only zooming in one particular aspect on principal component analysis. This is, it's always nice to have to be surrounded by lots of talented students, which are more talented than you are. So keep your scientific research program going on. So in particular, Dongwang was my postdoc, and these are, two of my very best PhD students. And if Penn State hire any of those, I can assure you will not regret. All right, so what is principal components? Why I focus on these issues? Why I have spent 10 years also working on these kind of issues, right? So it's really, if you're talking about what is the most fundamental tools for statistics, most people say regression. I know sample mean used probably more often, but regression is one thing that beyond the sample mean, right? So most fundamental tools in statistical machine learning is principal component analysis. For me, we do dimension reduction, and feature extraction, data visualization, and then being a financial economist, I spend a lot of time trying to understand what is the factors that drive stock up and down, rising tide, tide raise all the boats, right? And so this is trying to extract latent factors, and a lot of things that we are doing in applied math, if you through the lens of latent factors, a lot of procedures become very, very simple. Now, and of course, it's very useful for, I call precision medicine, really, clustering or like high-dimensional mixture models, right? And then it can be used to do social network. I thought I was giving talk on network today, but it's on district PCA. And then it can be used for various communications, videos, and so on. And why it's so popular? Is one of the non-convex problems. Ethan will laugh. I don't know as much computation issue as Ethan. So one of non-convex problems, we're able to find global solution within reasonable polynomial time. Right. So this is why. So whenever we cannot solve a non-convex issues like EM algorithm or K-mean, so what you are going to do? Say, hey, let's make it as a spectral problem, give you an initial value through this spectral method, and now you apply, whatever EM algorithm or maximum likelihood explanation. So now, what is knowledge? On this, right? So here is just one example. So how good can you estimate the first principal components? Right? So this is the first principal component in your large coherence matrix. The difficulty, of course, depending on how high dimension are you, right? So when you have a high dimension, D dimension, or there's a D components here, so you have square root D there, you have to be there, right? Depending on the sample size, everybody agree, and depending on the eigengap. Eigengap is really a signal to noise ratio, so it's depending on the eigengap. So these are really the three key issues. And I think on understanding the eigenstructure, starting from the Bartol's support, and there's a lot of studies on random matrices and so on. So we contribute probably one of those last efforts, just published in the Annals of Statistics on that. Now, the issue we asked today is, if data was scattered around on different machines, just like the San Francisco collecting all the data about Google, the New York collecting all the data here, Washington collecting their own data. So, and then each of those, I do principal component analysis. So at the end of the day, how good am I doing? So, so this is the question I'm asking. What is the distributed piece theory? How good can I do this, right? And here is the assumption that I made. So I have capital N sample, and store on n different servers. And for simplicity of notation, I assume that equally stored. It doesn't have to be so, right? And for simplicity of today's talk, and people who know me that I have done lots of robustness, I can really remove sub-Gaussian away, but I cannot keep adding structure to getting things complicated. So I just assume that each data on each machine is a multivariate of d dimension, and they are sub-Gaussian, so they behave like sub-Gaussian. And then the population covariance matrix is, have this spectral decomposition. And my interest is not estimating the whole covariance matrix, just like Google page ranking. I only want the first principal components, or for like the network study, like the community detection, I want second principal components, and so on. So I just want the column space created by those by these principal components, and the error measure is just the distance between these two spaces. So it's really some of those principal angles. Cosine of those principal angles angles, right? So this is the space that we are using, and this is independent of your parameterization. If you rotate your space, it's still the same that we are measuring. So here I assume the data really, is IID, right? So in each machine, but this can be generalized to heterogeneous case. So different machine has different covariance matrix, but nevertheless they share some principal eigenspace. And this is particularly useful when we talk about, let's say financial studies. And here is a very simple algorithm. The first machine has its data. You compute the sample covariance matrix, and then you apply principal components. So you've got the first k principal components, right? So the eigenspace of those first part of data, and the last machine you do the same thing, right? So now I get n different eigenspaces. So the next issue is how do I aggregate them together? And so what we do aggregate them together is just creating eigenspace by each machine, and now I just averaging all these D by D covariance matrix, D by D matrix, right? So each of those have rank k, right? So each of these has rank k, because I just take k columns and transpose times its transpose, right? Now I extract the common part, right? So the eigenvectors from that aggregated eigenspace or aggregated sub-covariance matrix. So now in terms of communication, how much do I communicate? Right? So each machine sending k eigenvector to the central server. So it's really k times d eigenvector. Let's say if you send in 3 eigenvectors, it's just 3d. So it's a vector d you have to do, right? And then what is aggregation means is really basically say, hey, I'm asking myself, I want to find an average in the sense that the distance between the space I want to all those spaces on average sense have the smallest distance, right? So this is really this guy was doing. Now the next issue is, economists would like to use the word spillover effect, right? So let's say I want 3 principal components. Now this machine may not necessarily the first 3 principal components are on this K1, right? There could be some leakage, right? So the first principal component, some part will go to the 4th principal component, some will go to 5th principal components, right? And the same with this machine. So instead of sending exactly 3 I want, I could send you more. I could send you 8 principal components, right? So this is what I'm trying to say is like, even though I only want 3 principal components, I could send A principal components to the central machine to overcome this spillover effect. And now I could still construct this, right? So this each of those would be like a D by D matrix of rank 8, right? So now I extract principal components, still I only want 3. So this would be the issue that deal with spillover effect, and the result continue to hold for that. So before we go on, people will naturally ask, why you are so silent about eigenvalues, right? So, then why we are all talking about shrinkage on eigenvalues, never people say shrinkage on eigenvector, unless I tell you eigenvector is sparse. If I don't tell you eigenvector is sparse, we all keep quiet and silence on eigenvectors, and eigenvector is really the one we want, right? So it's the principal components. And here, in dealing with distributed computing or distributed estimation, so this is the principle number 1. So average cannot be, bias cannot be averaged away. So if each of those machines estimate has bias, and let's say each machine has only 10 data points, right? Or 20 data points, which at the example I'll give you 20 data points. So the bias based on 20 data points could be pretty large if you believe asymptotic holds, right? Could be pretty large. When you aggregate, no matter how many machines, a million machines together, it will be still bias of all the 10 machines, sample size 10. So they cannot be averaged away. However, variance can be averaged away, right? So when each machine has high variance, and then you aggregate among those 10,000 machines, well then the average will be average, the variance will be averaged away. So therefore, if you start from an unbiased estimator, and then you do aggregation, doing average, at the end of the day you have little bias, little variance, you are smiling, right? So if you start from a biased estimator, the bias is at a very low resolution, and then when you do aggregation, it's still at very low resolution, so you'll never get it right. So it is very well known that eigenvalue is biased. The largest eigenvalue is way bigger than what you want. So for this reason, in doing these aggregations, we didn't even weight it by eigenvalues, just to make life simple. So we didn't do that to deal with the bias issues. And this is really the thing that I'm writing here. Now, I have said so much, and then there's a lot of literature, and a lot is much smaller compared with us. So it would be 1,000 times more literature than that. So that means they still have a lot of work to do, and I think I only wrote a paper before that with Heather and other people that on distributed inference that I presented briefly yesterday, but it will appear in the end of statistics. Okay, so now let's give you statistical error analysis, bias and variances issues. Right? So this is again the notation. Remember, each machine has I compute principal components, right? And this principal component is, and then I create a D by D matrix just by taking principal component at that. And now I take expected value of this. This is a notation I use called sigma star of rank k, right? Of rank k is a low rank matrix. So this is because I assume that I ID, so this L doesn't play a role here. So now this is your aggregated eigenspace, and this is the true eigenspace of population covariance matrix. I can always insert a term here just by using triangular inequality. So I get in 2 terms, right? This term is really the bias issues, right? So what is the target at the case level, and then what is the to the population what you want. So this term is called bias, and the other term is the average of this, right? Average of k machines to its mean. So this is the variance. So it's really I have bias and variance decomposition. So by just law of large number, you can easily imagine if number of machine n is large. So by law of large number, that will converge to its expected value, right? And so therefore, by using value type of theorem, you'll see that d variance equal to 0. So the issue is how big are they, right? So this is the first theorem that basically saying how big are they. So for each individual machine, so for each individual node server, and this is the target individual node server is calculating. So how far these two eigenspaces can be, we basically say depending on the sample size each machine I use little n. K is the number of principal component I'm extracting. R is also called effective rank. So really the L2 norm divided by this, or if you like, if I put in square inside, it is smaller or equal to the traditional definition of effective rank. So it's really just the trace divided by the maximum of eigenvectors. So it's really the effective rank if you compute it. So this is for each individual machine. So if I average it over m individual machines, as you would expect, right? So it would be just n times smaller, and this is just the eigengap between k's principal component and k plus 1 principal components. And here I introduce a little bit called psi 1 norm, which really the same as what traditionally we say, of order OPAN, except that I also require tail to be exponentially decay so that I could deal with the maximum error. So now here is the analysis of bias, and this is really, I think, probably the most fundamental new story to the question I raised before: why we are serious about eigenvectors. Right. So this is the target of each machine, right? And this is the one we want. Right? How different are they? And this is the algorithm we do. Right? So each machine, you compute sample coherence matrix, you apply principal components, you extract the first k eigenvectors or eigenspace, and now you take expectation. The notation I give this a name called sigma star. So sigma star, have this decomposition of the first k principal eigenvalue. So this is one operation. I take principal components first and take expectation. Right? So the other operation is I started from this. I take principal components. I got sigma, right? I got the population coherence matrix. Now I take principal component of this population. Principal component is the target I want, right? So these two operations just change principal component with expectation. And we all know that principal component is highly nonlinear, right? So is it exchangeable? Right? If exchangeable, it becomes unbiased. So my question is very simple. Are those two guys the same? Taking principal components first, and then taking expectation, or taking expectation first and then taking principal components. And it turned out that they are actually indeed the same with a very small and weak condition. And the condition is this, right? So let me define a vector of d-dimensional to be symmetric. If you flip a sign of any of those components, the distribution remains the same. Right? So like T distribution, Cauchy distribution, multivariate ellipsoid, spherical symmetric distribution, elliptical distribution are all symmetric. Right? So now if I say X has a coherence matrix sigma with the symmetric innovation, means that if you spherize or standardize the coherence matrix, the resulting matrix is symmetric. So in other words, if you take a symmetric, you do affine transform, and you get the coherence matrix, and that matrix we call, that result we call have symmetric innovation. And then we basically have this theorem, basically saying that as long as your data have symmetric innovation, then it's unbiased. The bias is zero. So the operation highly nonlinear. Principal component first, expectation first, followed by principal component. They are unbiased. So if it's unbiased, then everything is very nice. If I just summarize those together, I will get a very nice result. So for general, so if you don't really have symmetric innovation, and if you imagine you do Taylor expansion, you can easily see that the eigenspace also has very small bias, second order nature. Right? So this is the sample eigenspace in the case L machine, right? And this will be the first term. So if you have consistent first term, then the next term will be a linear function of, right? This is a linear function of your sample coherence matrix, linear function of population coherence matrix, right? And then plus the second order square. So now if this guy, each of these machines give you a nearly unbiased estimator. If each of these machines give you an unbiased estimator, then it's easy to see if I take expectation here, you will get in, right? This is what you want, and get in the second order nature. Right? So this is what I said. So you'll see that the one that you want is of second order nature, and this is really the more formal theory. Basically saying, for a general case, you are getting the second order nature of the bias. So now if I, and this if I summarize, this is really a kind of second order Davis-Kahn type of theorem, basically saying that this is sample you want, this is population, and you minus a linear operator, you will be controlled by the second order, and not once you take expectation, you're getting this is zero, so you're getting bias of second order nature. So again, let me not get into too deep on that. And very lately, we have even more results about the eigenspace and eigenvectors and how to linearize all those eigenvectors and its application to community detection, top K ranking, and so on. I put it up last night, but I didn't realize that we need to go at the end, so let me skip it for now. If we interest, I'll come back. Right? So now if I put in these two pieces of results together, bias can be averaged by, just by the usual. No, so bias is zero, so there's no bias there. Right, so variance can be averaged away. So if I do this for symmetric, the data with symmetric innovation, your error really is having variance here. So for a more general case, you could control like variance and bias. And now you can see that the bias is of second order nature. So as long as the number of machines is not too big to make this one too small, right? So then variance will be dominant. So in other words, as long as variance is dominant, then even though you do not own the result, the data, your estimation result is as good as if you own the same data. So in other words, we obtain the same rates as principal component analysis with the whole data, even though I do non-invasive analysis of data. And this matching with lower bound derived by Tony, Kai, and Harsh and Zhou, and so on. And we require minimum sample size on each machine. We can show this is sharp. If not, I can give you a counter example. You can do that. And we also extend these to heterogeneous data. So this is really a little bit more saying about heterogeneous data, meaning that each machine has different covariance matrix, but nevertheless they share the same eigenspace, just like each machine stores certain kind of stocks. Right? So each stock are different, but their volatility, individual stocks are different, but the factors that drive market independence are the same. Right? So this is really what we do, approximate to the approximate factor models, and we could get all those similar results. And I believe that whatever I talk is better illustrated when I do a simulation study to illustrate that. Right? So in this simulation study, I generate d-dimensional Gaussian data. And these are three very spiked eigenvectors. Right? So in this case, I'm making eigenvalues, so it is lambda, half lambda, and 1 in the minus 1. So there are three principal components. And the theoretical eigenvalue is the first coordinate, second coordinate, third coordinate. Right? And the eigengap is this. Right? So this is the eigengap. And then, of course, when this lambda is large of dimensionality, you can easily use in the theoretical result we showed before. The accuracy depending on dimensionality, the total sample size, like m times n sample size, right, and then d. And then we do this like simulation for 100 times. And now I examine statistical rates, right? So I verify that if among so many things, I take log of this, right? So it would be the slope would be 1/2 on dimensionality, negative 1/2 on number of machine, negative 1/2 on sample size, and negative 1/2 on delta, right? And so on. So here I'm showing you basically say, let me see the effect of dimensionality d. Right? So I take the log result of d, and then this is for 5 machine, 10 machine, 20, 50, 100. So the slope here is all about 1/2. Indeed, it's very close to 1/2. Similarly, if I fix the remaining other things, but just see how it depends on the number of machines. So this is for different dimensionality, 100, 200, 400, and so on. So you can see all those rate, it's 1/2. So in other words, if you look at all these, so the rate that we're showing you is correct. Now if I do this, I think this slide probably illustrates a lot what I really want to say. So in this case, I fix the total sample size to be 6,000. Okay, so total sample of 6,000. So when I have only one machine, that means I own all the data, right? So everybody commit data to me, and this is really the log m equal to 0 that I have here. So in this case, this is for d equal to 100, 200, 400, 800. But as dimension increases, we know it's getting worse and worse. That's because the sample size is fixed. Right? And now as number of machine increases, let's say to the extreme here is 300. So when I have 300 machines, each machine has only 20 data points. And if principal components were biased, then the resolution would be biased at sample size 20, right? And then when you aggregate, averaging over 300 machines, the bias would be dominated by the sample size of 20. Right? But from here we can see, as number of machines increases, the estimation error based on 20 on each piece of machines, as well as if you own all those 6,000 data. So this example showing exactly by adaptivity. Even though data was disputed into 300 machines, each machine as low as 20 data points, the estimation effect is the same as you own 6,000 data. So this sort of, as I said at the beginning, non-invasive analysis, because I never own your data, I only ask you to tell me the principal components, right? Solve computation issues. So if everything here is scaled by 1,000,000 times, you still solve computation issues and storage issues and so on. Right? So this is one example we show you this. Now the next one I will just show you really the same. Right? So as I said before, the statistical rate of convergence technically is like this. Now we take a log and now regard this as a multiple regression issues, right? Because there's multiple parameters there. And so I regard it as multiple, right? Number of machines, local machine data sample size, eigengap. And now I figure multiple regression through different kind of simulation, different kind of combination of that. And the result was surprisingly consistent with the data. Of course, if you with multiple R square looks like this, of course you'll fit the value and the true value looks like that, right? So now the next issue is I want to show you the last idea of spillover effect. Right? So we want to examine spillover effects. So I'm always afraid of information leakage. Right? So the top 3 eigenvectors may not necessarily 100% contain in the top 3 sample top 3 eigenvectors. So therefore, I do just the first one, just distribute PCA. If you want 3, I give you 3. Right? So the second one is full sample size, so you own the whole data thing. So as if you own the whole data. And the third one is I want 3 principal components, but nevertheless, I ask the machine, please send me 8, right, rather than 3. So I feel safer if you send me a few more, right, safer. A little bit more communication, safer. Right? So I want to examine what is the spillover effect. So if I give you a very spike-rise matrix, like lambda equals to 30, so it's very spiked. And now you can see all those 3 methods. There are 3 methods. You cannot see the difference because they are. If you look as close as I have, there's small difference. Right? So, but you cannot see the difference. So basically, we're saying there are very little spillover effect because the first 3 principal components contain all. Sample principal component contain all population principal components. So more or less, for different number of machines, they are working more or less the same. Now I give you a weaker signal, right? So lambda equal to 6. So when lambda divided by 4 minus 1 is equal to 1.5. Right? So 1.5 is a little bit spike, but very small spike. So in this case, of course, whole sample, if you own whole sample, this is your estimation error you have. So if you really only communicate 3, then some of those sub-servers will have leakage effect, right? Some of those top 3 principal components maybe go to 4th, 5th, and 6th, right? And so on. So you can see as the number of machines increases, the average bias increases substantially. So if I communicate 8, then I think the all information is still very little leakage beyond the 8 principal components, right? So as the number of machines increases, so the statistical estimation error doesn't change very much. So it just demonstrates that effect. So now let me conclude. What I have taught so far. So first, when we deal with distributed computing, and this is principle, principle number 1 in this class. I even tell students of elementary studies class, right? So bias cannot be averaged away, right? So bias is an important issue in distributed computing because later on when you aggregate it, variance can be averaged away, bias cannot be averaged away. So, the second one, now at least I give you an answer. I want you to hear silence on shrinkage on eigenvectors, unless you assume sparse. If you do not assume sparse, I rarely hear people talk about shrinkage. We basically say distributed PCA is an unbiased estimator when data has symmetric innovation. And in general, the bias is of the second order nature. And because of that, when we do aggregation, we didn't want to use principal components. So eigenvalue, because eigenvalues are biased. And then I say distributed principal components has aggregated variance effect. This is not surprising, but still mathematically you have to show that, right? And at the end of the day, we basically saying that because you are unbiased or little biased, and you have aggregated variance effect, so even though you do non-invasive analysis of data, at the end of the day, you still get the same performance as if you own the full data sets. And that's all I want to say for today. Thank you.
Any questions?
So oftentimes people don't necessarily say I want 3 principal components. They'll say I want 85% variance or EIC calculation or something. So do you think that this would have any effect on these results?
Yeah, no, I mean this is a very good question. So so the answer is yes and no. So if 85% is contained by, I need to use, let's say, 70% of eigenvectors. Well, I mean, sure, but then my eigengap would be very small. So the eigengap would be very small, so I think it will be affected. But if the 85% is contained in top few eigenvalues, so that they have reasonable gap, I think it will not be affected. So so this actually you really come to the issue, right? So probably you need to communicate further. How do I choose, let's say, a number of eigenvectors, and you also prompt to the next issues, how do I estimate the eigenvalues of each of those components, or of the whole sample points matrix. So these are interesting questions. We didn't really get to that kind of study, but I think it's possible.
In aggregation, I think the simple average will be used. Do you think it is possible to develop a new averaging method to improve the performance?
So you might thinking of, let's say, other centroids. For example, the average is using L2. So today's talk, right? So average here is really using like L2 distance. So we are really computing the centroid by using L2 distance. So if you can take the square away, or are you using other things? So yeah, I think it could have effect. As I said, in analysis here, we assume data are Gaussian. So therefore, I think average is the best one we can do. Right? So when data are not Gaussian, yeah, you could try to do like what you say, let's say take the square away, or actually in the past few years we developed systematic methods. Even though data here starting from with the second moment, in this case it's fourth moment, the second moment is already commented. The data started with fourth moments, and we do, let's say, either truncation or adaptive human type estimation. So at the end of the day, the covariance matrix here, the inputs you get here, would be very similar to have, let's say, like a sub-Gaussian behavior. But now, of course, there's an issue. Once I do whatever truncation of this guy will be biased. So the bias will be carried over. So new studies really need to be more carefully studied if you are willing to move away saying that the data doesn't have sub-Gaussian. Once average being moved over, what I'm trying to say is to have two effects, right? So one effect is is on estimating this correlation matrix. Some LCD mode away is on estimating correlation matrix, and second one is on this aggregation. Yeah, so it will be an interesting question to look at.
So do you need a computation on eigenvalue? So
就
在你就在 computation 里面，常常性的这个看 correlation so one eigenvalue 多属于注意体的，在原生多属于注意体。
Right. So this is again very good question. So do I consider condition on eigenvalues? So we indeed do. It's just implicitly writing here. So this eigenvalue, the eigengap I say here is let's say the bigger you get, the better you got a stronger signal. And this is the largest eigenvalue. This is the differential. So in, let's say, factor analysis, or economists call pervasive factor, so a factor influence a large fraction of stock market, or a factor influence all different sectors, like federal, let's say, monetary policy, or like biology, people thinking that if I give, let's say, special treatment, let's say some kind of drug treatment, raise all the gene expressions. So when factors are pervasive, so it can be shown that the maximum eigenvalue is of order d, the same as the dimensionality. And then this eigengap, if you really think there are only k eigenvalue, this eigengap is also of order d. So these two can cancel. So eigengap, those will be of the same order, but we do consider the eigenvalue probability. So it's embedded in this expression.
I have a question. So if you consider sparse framework, so and each estimation is by some, say, convex relaxation by Mas-Fremont's framework, and so then you take average, but doing some hard computation, hard thresholding will lead to the optimal statistical error.
Yeah, so you asked a very good question. So let's go back to the basic again. Right? So very good question. Again, see, we need talented people like you to all work together. Right? So now in this case, let's say suppose we have sparse eigenvector to begin with. Right? So there are two operations you can do. Right? So first, you get to this part, you can do sparse PCA. Now you get this V1, right? And then you get sparse PCA, get this V1. Now you can aggregate this. Now this will destroy its sparsity, but nevertheless, hopefully, good ones still remain big, right? And then you do truncation. That's what you said. Right? Another thing is that I just do what I say to here, right? I get to this part. So at this part, still unbiased, right? To this part, I'm still unbiased. To this part, I'm still unbiased. Now I do sparse PCA on this part.
Okay.
I don't know which one is better. I probably prefer this one because, as I said, bias make me nervous when you aggregate over machines, right?
Yeah.
So let's get in variance reduced first before you reduce bias. Right? So this, I don't know, to always maybe we could do something. I see. Yeah, that's a very good question. But that's what I would like to do. Let's aggregate first for unbiased, because bias is always making me nervous. Right? It cannot be averaged away, and then do sparsity.
Would it help if you make several layers of aggregation? Let's say first I aggregate 100, and then three covariants, then you aggregate again.
Yeah, this is very good question. I know what intuition you have in mind, right? So let's say suppose data is stored all over the place, right? So you would like to aggregate data, let's say around San Francisco area, around New York area, Washington area, Philadelphia, and so on. So really what you have in mind is heterogeneity. Right? So if there's no heterogeneity, you don't really need to divide these into. So when data has heterogeneous, and this heterogeneous depending on the location or in some way depending on one dimensional that you have in mind. So I think in that case, probably that localizing it, and so for example, aggregate local machine will give you benefits on bias on the bias issues. So I think in that case, so at this moment, I mean. When we finished this, actually, I was always more interested in doing more heterogeneous data. I really haven't been able to do very far away from heterogeneous. So when I do, so we do heterogeneous, but not as heterogeneous as we would like to have. And then, as I said, we spend like the last 10 years also doing all those random matrix theories, that's why these pure random matrix theory, and mainly because our application driven by two very important facts. Right? So all financial applications require large coherence matrix in order to understand the risk, to understand the optimal bottom allocation. When we control for discovery rates of let's say, large-scale hypothesis testing, so you need large coherence matrix inputs in order to control the rates correctly. Or if you have latent factors, you extract those latent factors, then the data be as if they are independent. So in most of our analysis here, I really have in mind is they are the same biology, right? So the lab in Penn State, the lab at Harvard, the lab at Yale, they have similar science. So in that case, then you just aggregate those together. But if you are really thinking of heterogeneous across different regions, we have to be more careful. And we haven't gone to that stage, and I welcome someone like you, having dealing with, different kind of principal component left and right, to contribute to that. Yeah.
I have a big picture question. So in statistics, we spend a lot of time thinking about estimators with optimal convergence rates. I have my new estimator and it's better than your old estimator. So as data sizes get larger and larger, how relevant is that? Think about optimality and efficiency, as you said.
Yeah, this is always very good question, and I like that question. I think of that question myself too. But it's always interesting. We all, being as a statistician, we're always doing a right signal to noise ratio. Right? So when signal to noise ratio is too low, nobody can do anything about it, and it's too high. Everybody who improve math can do it. Right? So when sample size is getting bigger, we accompany with it the dimension also getting bigger. So it's somehow like this. So the ratio, perspective ratio, come into play. So this is why I'm saying that even though when we're talking about, let's say, distributed inference, so you're thinking about you have billions of data, but also thinking you have billions of dimensions, just to make your signal to noise ratio not as easy, otherwise it would be trivial. Well, otherwise, even not efficient method would be giving a very precise estimate.
Yeah, so,
Sorry.
So there are routines for calculating your sample covariance across distributed data, but I'm guessing you're not doing that because of computational reasons. But it seems like you're still on each machine dealing with a covariance matrix of the same size that you would be if you calculated distributed and had it at the central node. So it seems like you're running into the same computation issues still because you still have to work with really large covariance matrices. So what is the computation that you're saying?
This is a good question. Right? So you're basically saying that there are two ways. Right? So one way is that you can ship all the data to the central server, right? And the second one is that everybody compute that and send to the central server. So in my the advantage of what we are doing here is first, that's the communication. So if you send me a billion by a billion coherence matrix or 10,000 by a million by a million coherence matrix, that would be taking hours, if not days of communication. I don't know, I didn't calculate. You may be able to go back and calculate how long it will take. Using current bandwidth that we have, it would be very, very long, if not a year. It's very easy getting to that automatically. And then the second one, being as a statistician, I also want to contribute positively to the big data issues. And the big data issue is, as I said, I talk to people, let's say in the paradigm of, let's say, Shanghai government. So they are very, very concerned about privacy and ownership issues. So if you ask hospital, Harvard Hospital, to give me the data for me to analyze, I'm pretty sure they will refuse. And the same Penn State, even with the friendship, they will refuse. But if I say, hey, here's the code, you could shut off the machine, you run it, and then just report the result. If you really don't like, I could even provide the machine after you run it, you just destroy the machine. Right? So I could get in the result, and I only aggregate the results. I never touch your data. So this actually contributes very positively to the big data efforts that on privacy issues, on ownership issues, and that's actually also another reason I'm thinking of, let's say, distributed analysis of data.
Well, just to clarify, I wasn't saying you should put all the data in the same place. I was saying there are methods for calculating the sample covariance without sharing the data, right?
Sure. I mean, sure. But again, you have communication issues.
Right. You still have to send the
Yeah.
covariance.
Yeah, right. And this covariance, as I said, is also, I mean, very expensive. I do not allow myself to send d squared. Let's say entries over the internet. I only allow me to send a linear, like k times d. Because I have to send an eigenvector over, so at least I have d. So it's a k times d is allowed, a d squared is not allowed. So that's the limitation that I have in mind.
No more questions. Let's thank our speaker again.